Kia ora. In the last video, we discovered an important constant together. Written with the letter gamma, the Euler-Mascheroni constant is defined as the limit as n goes to infinity of the sum from x equals 1 to n of 1 over x minus the natural log of n. If you have not seen that video yet, I highly recommend watching it first. In the rest of this video, we will use a lot of visuals, ideas, and identities from that video without explicitly explaining them here. We saw that this sum can be nicely visualized as the sum of these small areas that fit inside a 1 by 1 square. I must now admit that in my last video there was a small mistake. The visual I created was taking the sum up to n of 1 over x minus the natural log of n plus 1. Since this is a limit as n goes to infinity, the limit was still an accurate representation of the Euler-Mascheroni constant. But for the rest of this video, it will be important that we're using ln of n plus 1, since we are approximating the value of gamma. Last time I posed the challenge to find an approximation for the Euler-Mascheroni constant using the first n terms of the sum that is more accurate than the nth partial sum. There were multiple great responses to this challenge, and with a few exceptions, they essentially came down to adding one extra term. This term somehow can make our approximation orders of magnitude more accurate for any given n. Let's go on a journey together and figure out what this term could be. I would like to point out that there is not one single value for this function, as there are many ways to approximate the Euler-Mascheroni constant. If you come up with a different approximation, I recommend checking it against the accuracy of the one that we will come up with in this video. If it's more accurate, let me know about it in the comments. To begin our investigation, let's take a closer look at each of the little slices of area we have created and see if we notice anything. Let's take the first two slices as examples. Hopefully we can find some patterns that can be applied more generally to the nth slice. The length of slice 1 is 1. This is because it goes from x equals 1 to x equals 2. The length of the second slice is also 1. This is because it goes from x equals 2 to x equals 3. Slice n goes from x equals n to x equals n plus 1. Therefore, its length is also 1. The top of slice 1 happens at y equals 1. This is because of how we defined the rectangle that this area slice came from. The top of slice 2 is at y equals 1/2. Once again, this comes from the definition of the original rectangle. Similarly, the top of slice n is at y equals 1 over n. The right edge of slice 1 is at x equals 2. And the bottom of the slice is defined by the function y equals 1 over x. We will be precise and use the fact that 1 over x is a monotonic function for x is greater than 0. That is, it's a function that is always decreasing from left to right. That tells us the minimum of the slice comes at the right side of the slice. Therefore, the bottom of slice 1 is at y equals 1/2. We can use the same argument to find the bottom of slice 2. Since the right edge was at x equals 3, the function 1 over x gives us 1/3 as the value at the bottom of this slice. The same is true for all the slices in general, where the bottom of slice n is at y equals 1 over n plus 1. This gives us enough information to determine the height of the slices. For the first slice, the top is 1 and the bottom is 1/2, meaning the height is 1 minus 1/2. Yes, this is equal to 1/2. However, We're going to keep it written as 1 minus 1/2 for a few reasons that should become clear in just a moment. Slice 2 has its top at 1/2 and its bottom at 1/3. Its height is 1/2 minus 1/3. The height of slice n is 1 over n minus 1 over n plus 1. Now that we have all the dimensions of these slices, let's create some rectangles around the slices to help us consider the relative size of each slice. The sum of the areas of all of these rectangles is 1, which is important to establish. This can be seen in two ways. If you consider the sliding that we did with these slices before, if we fill in all the extra space, it is clear that the total area is 1. Alternatively, it can be seen that the sum of these areas creates a telescoping series whose first term is 1. Notice that all of the slices take up more than half of the area of their rectangle. If you're up for a challenge, justify how we can be sure that this will be true for all slices. Tell me what you come up with in the comments. This should convince you that the total area of all of these slices combined is greater than 1/2, and thus is a nice solution to one of the challenges from last video, asking to justify why the Euler-Mascheroni constant is definitely greater than 1/2. Also notice that these slices are getting closer and closer to being exactly half of the area of the rectangle as n gets bigger. To state this more precisely, the limit as n approaches infinity of the ratio of the nth slice of area to the rectangle it fits inside is equal to 1/2. Another challenge? Prove this limit using L'Hopital's rule. It is a good exercise in algebra and differentiation. This might seem like an overcomplicated mess, and that's because it is. It is just a mathy way of saying exactly what we just discovered, that these slices get closer and closer to taking up exactly half of their respective rectangles. This is a great opportunity to pause and consider what we have done, what we want to do, and how this information could be helpful in accomplishing that goal. The beautiful thing about this limit is that it means we have a nice approximation for the rest of the terms in the series that we don't directly include in our partial sum. If our sum is the first n terms, we can add half of the remaining area to make our approximation more accurate. This gives us our approximation sum. As you can see, if we add 1 over 2 times the quantity n plus 1 to our first n terms, it is significantly more accurate than just taking the first n terms of the series. That wraps up our investigation on the introduction and approximation of the Euler-Mascheroni constant. In the next video, we will be solving this integral. Give it a try and come back to check your answer. I hope to see you then. Kakite.